So let's begin, everybody. Welcome to our maths class today. Today we're going to go through 4C and 4G. So 4C is going to be quite short. We have, I think, 2 questions to do from it. We'll start to develop some proof techniques. And then 4G, we're not really going to learn anything new in 4G. Rather, we're going to apply the rules that we learned in 4C. So this here is called the fundamental theorem of calculus. And what we've been doing so far is we've been learning the rules of integration. So we've been integrating f of x with regards to dx, and we haven't had any boundary on it. Now you might remember right to the start of the chapter when we did exercise 4a and we were doing area under the curve, right? And you might remember the integral from a to b of f of x is going to be the area under the curve f of x. Okay, so here's some function, and we have from a to b, then the area under the curve from a to b of f of x is going to be this, what we call a definite integral. Definite because it has boundaries. It has a lower boundary and it has an upper boundary. This one is indefinite because it does not have a boundary. Now, we know when we use an indefinite integral, we have to go plus c at the end. One of the key differences is that with a definite integral, we don't need plus c, and I'll show you exactly why today when we go through our answer. So if we have the integral from a to b of f of x, I've said that's going to be the area under the curve from a to b. Capital F of x means the antiderivative, right? And we're going to put that in square brackets with our boundaries listed here, and then we sub in the upper boundary, and we take away the lower boundary. So let's just read through the first example that I've presented for you there. So I've even typed it out for you. So it says, find the area under the curve y equals x to the power of 3 from x is 1 to x is 3. So the first thing we've got is a definite integral statement. Do we see that? Integral from 1 to 3. There's the function with regards to x. Okay, and alongside on the right, all I've written out is the general form of it. Integral from a to b of f of x. Okay, then we integrate it. So the integral of x to the 3 is going to be x to the 4 on top of 4. That's going to go in square brackets. And we have the lower boundary at the bottom, the upper boundary at the top. Okay, so that's going to be the second part. That's this part of the fundamental theorem of calculus. Then we sub in the upper boundary here. So we have, when we put 4 in, and the lower boundary here. So we have the upper boundary, take the lower boundary. And then we've just evaluated it, 20 units squared. Okay, let's do part B together. All right, so we'll apply the fundamental theorem of calculus here. It says, find the area under the curve y equals 2x plus 1 from 0 to 2. So we're going to integrate from 0 to 2, and the function that we're integrating is 2x plus 1 with regards to x. So we're just going to follow the formula through, right? This is the first step in our fundamental theorem of calculus. Then we'll move on to the second step, which is where we're going to have the integral in square brackets. So the integral of 2x is going to be 2x squared on top of 2. All right, so the 2's hangs out. The integral of x is going to be x squared on 2, and we can simplify that in a moment. All right, and the integral of 1 would be plus x. And I'm going to show you why we don't need plus c when we have a definite integral. And I'm going to show you why by putting it in there. Okay, so we have, that's the integral function, and we're integrating over the boundary from 0 to 2. All right, this term here, this is just going to simplify. We have 2 at the top, 2 at the bottom. And so we're at this step at the moment. So now we're ready to move on to here, which is where we're going to start by substituting 2 in. So we would have 2 squared plus 2 plus c, take away, and then we're going to sub 0 in, right? So we would have 0 squared plus 0 plus c. Okay. So this part here is going to become 4 plus 2, this part here is going to become 6 plus c, and this part here is just going to be take away c. And this shows you why we don't need to put plus c, because we have c, take away c, which gives us 6. Okay, so that's going to be the area under the curve from 0 to 2 is going to be 6. Now, while we're just looking at this, let's show you how we can use our calculators to evaluate it. I'm going to show you two strategies on the calculator, so you can pull those out. No, it's not going to make a difference unless you're doing a trigonometric calculation, and then it will, because your boundaries will be set in either degrees or radians. But remember, we said 98% of the time you're in radians. So just in your run map, we can go option, calc, and you should see an integral button. Okay, option calc, and we have this button here, integral dx. Alright, so we press that, and all you would do is type in this expression, integral from 0 to 2 of 2x plus 1. What do we think it's going to equal? 6. Good guess. Excellent. I got 6 and I value of 2. Alright, so that's one way we can use the integral. There's going to be another way as well. So let's go to our graph menu and we'll graph this function, 2x plus 1 over a standard V window. So 2x plus 1, set our V window to standard. Alright, so it's the equation of a line.
How do we do that again?
V window is F3, and just press standard for minus 10.
Like, put it on the graph function.
2x, y equals 2x plus 1?
Options.
Yeah, I'm in there.
Yeah, and so when we're in graph mode, we can go G solve, which is F5, and if we press the across arrow, you'll notice there's an integral button. Okay, we have integral dx. Now, the main one we're interested in at the moment is going to be F1, which is just integral dx. Okay, and if we press that, what it wants us to do, it says right at the top, select the lower limit. So I'm going to press the number 0 and execute. And then it's going to want me to set the upper limit. I'm going to press the number 2 and execute. And it even shades the area for you. So I've got the integral from 0 to 2, and it tells me what the integral evaluates to. Okay, so a few instructions there. Did anyone get lost along the way?
No, we're
Worked it out? Claire, sorry, Sammy, you okay? So G solve, across, and then integral again, and then type in 0, enter 2. Yeah, Shreya, you're good? Excellent. Hugo?
Insane.
Insane, did you say?
So can you please? Got that one.
Oh, now, you don't type in the whole thing. All you type in is the equation, just 2x plus 1. Yeah, that's all we want. And then you have G solve, integral, from 0 to 2. I'm just going to shade it.
Easy. Thank you.
Excellent, no worries. Okay, good. So a couple of ways we can use our calculator there, but in a moment what we'll get you to do is a few examples of these. But we do have one more example, which is a proof, all right? And question 4 in this exercise is largely about proofs using the fundamental theorem of calculus. So we're going to go through the first one together. All right, so we're going to talk about how to do a proof, how to communicate it, because in this test there will most likely be a question about proving one of these properties. All right, now I'll leave that up there because we are going to apply this in a moment, this whole thing. Okay, so we are required to prove that. And we have the integral from a to b of k with regards to x equals k times b take away a. Okay, now with a proof, what we need to do is we need to show that they're the same. Now we can do that by manipulating the left-hand side until it's the same as the right-hand side, or manipulating the right-hand side until it's the same as the left, or manipulating both until they're the same. We just need to show that they are the same somehow. So here's what we're going to do. We're going to start with the left-hand side, and all we're going to do initially is make a statement about what the left-hand side is. It's the integral of k with regards to x, where k is some number. Okay, now the integral of a constant is going to become kx, right, from a to b. Okay, so we're just applying the fundamental theorem of calculus here. Now, when we sub in the x value, what this would equal, it would be k times b, take away k times a. Okay, so now we're at that step of the fundamental theorem of calculus, and we're very close. Okay, we're very close. All we would do is factorise k, and we'd be left with b take away a, which equals the right hand side. Okay, remember for a proof or when we've done a first principles or shown that they're the same, we've quite a right to demonstrate, we've shown that it's true. Okay, so that's a perfectly suitable way for proof. Now, I just want to make another case as well, is that I've started with the left and manipulated it until I've got to the right. Another thing we can do, let's say that we got to here and we couldn't really see a link between these two steps. So one thing that we could do, yeah, come in, mate. Thank you. One thing that we could do is we can start with the right-hand side and say, well, how can I adjust the right-hand side? Well, I could expand this, right? We could have k times b, take away k times a, and then you might go, oh, actually, they are the same. Look, I've shown that the left-hand side equals the right-hand side. So it doesn't need to be just manipulating left until we get to the right. You can manipulate both, and if we're at this step and we've shown that, excuse me, and we've shown that the left-hand side equals the right-hand side, we've proven that the relationship is true. So that'll be a good, thank you, that'll be good questions to work through. Okay, so let's go to 4C, and if we look at our what we're required to do from 4C, we just have question 4 and question 5, all right? So 4C, question 4 and 5.